Okay, students, now we'll study about the elongation of a bar with continuously varying cross-section. So here you have given a tapering rod. Here you can see a tapering rod here. This is a tapering rod having a diameter d1 at one end, and it tapers uniformly to a diameter d2 at the other end in a length L as shown in figure. Its modulus of elasticity is given as capital E, the material, and you have to find out what is the change in length when subjected to an axial force P. Okay. Now in this case where the cross section varies continuously, we have to take an elemental length. Okay. Now we can see here you have to consider an elemental length of the bar, and a general expression for the elongation of this elemental length is derived first. Then this general expression should be integrated over the entire length to get the total elongation of this tapering bar. Okay. Now here you have given a uniformly tapering rod. So first of all, let us write what is the change in diameter in length L. What is the change in diameter in length L? In initial diameter or the larger diameter is D1. It is given as D1. The larger diameter is given as D1. Okay. And the smaller diameter is given as D2. So what is the change in diameter in length L? The change in diameter in length L equal to D1 minus D2. Okay. Change in diameter in length L is equal to D1 minus D2. Therefore, the rate of change of diameter in length L, let us represent it by small k, which is equal to D1 minus D2 divided by capital L. Okay. Now you consider an elemental length of the bar dx at a distance x from the larger n. So you consider an elemental length dx at a distance x from larger end. At a distance x from larger end. Now we can write what is the diameter in this. What is the diameter at this section? At the section at a distance small x from the larger end. So what is the diameter? Small d is equal to, you know, k is the rate of change of diameter for L length. So what is the rate of change of diameter in x length? It is kx. So it has changed from d1 to k into x. So the diameter is d1 minus k into x. That is, small k is the rate of change of diameter for L length. So for x length, what is the rate of change of diameter? K into x. So the diameter is d1 minus k into x. The rate of change of diameter for x length is k into x. So the diameter of this elemental at this portion where we are considering this elemental length is d1 minus k into x. So you can write the cross-sectional area. Cross-sectional area, capital A, is equal to pi d square by 4. So which is equal to pi into d is d1 minus k into x the whole square divided by 4. Now we can find out what is the elongation of this elemental length. What is the elongation of the elemental length equal to you know the equation PL by A. P into, here L is dx divided by area is pi by 4 into d1 minus k into x the whole square into E. Okay, this is the elongation of the elemental length. So how will you find out the elongation of this whole length? It is integral of 0 to L. Length changes from 0 to L. That is, here you have dx. So 0 to L is the limit. So let us write now what is the elongation for this whole length. So we can write the elongation for of the entire bar. Elongation of the entire bar, let this be delta L equal to, we have the elongation for the elemental length dx, integrating it from the limit 0 to L, integral of 0 to L p into dx divided by pi by 4 into d1 minus k into x the whole square into E. So we can take the constants outside. So this becomes 4p by pi E into integral of 0 to L dx divided by d1 minus kx the whole square. Now you know what is the integral of x raised to n equal to x raised to n plus 1 by n plus 1. So integral of 1 by x square equal to minus 1 by x, because this is actually is equal to integral of x raised to minus 2. That is, integral of x raised to minus 2 is x raised to minus 2 plus 1 by minus 2 plus 1, that is minus 1 by x. So here we can write the integration as, integrating this you will get 4p by pi E. Integrating this, here you will have minus k into minus 1 into 1 by d1 minus k into x 0 to L. So you will get this as 4p by pi E. Instead of k, we have already this equation. You have small k is equal to d1 minus d2 by L. So we can substitute here. Instead of this k and minus k and minus 1 cancels, so it becomes k. K is equal to d1 minus d2 divided by L. So let us apply the limit, upper limit, applying upper limit, this is 1 by d1 minus k into L minus upper limit minus applying the lower limit 0, 1 by d1. Now from this you can write k into L is equal to d1 minus d2 or d1 minus k into L is equal to d2. So let us substitute this value here. So substituting, you will get 4p by pi e into d1 minus d2 divided by L into 1 by d2 minus 1 by d1. Okay. Now on simplifying, you will get this is equal to 4pl by pi e into d1 minus d2 into d1 minus d2 divided by d1 d2. Okay, so what you will get the equation? You will get the equation for the total elongation. Let us designate it as total elongation delta L is equal to 4EL by pi E into d1 d2. Okay, so this is the elongation, total elongation for a tapering rod. Now if you have a rod like this which has uniform cross section subjected to load P, you have the equation for delta L as PL by A into E. Here A is PL by pi d square by 4 into E, which is equal to 4PL by pi E into d square. Okay, now you can have a comparison here. Delta L equal to 4PL by pi E d square, and here it is 4PL by pi E into d1 d2. So you must remember this by heart, this, because there will be university questions and the question will be like this. Here you will have a cross section which is uniform, and you will have section like this which is uniformly varying, and the load will be acting like this. And in this case, first case, you will have to use the first equation, 4PL by pi E into d square, and the second case you will have to use the equation 4PL by pi E into d1 d2. So let this be d1. Here the diameter is d1, and let this diameter be d2. Okay, in this case you have to use this equation. So this is question which is usually asked for university examinations. So you have to by heart this equation also. Thank you.